Can you see my screen?
Yes, sir.
All right. So today we'll look at mean Melo theorem in one variable again in the context of multivariable, and we'll use it uh, to find differentiable functions from partial derivatives. I mean, to give a condition uh, on the function on the partial derivatives of the function, so that function becomes differentiable. The whole function becomes differentiable. So today is which date? 9th. Yes. So suppose f is a function from, let's say, Rn to R, right? And you consider the function. So let a belongs to a equal to a1, an is a point in Rn. And now if you consider the function, the following function, x goes to f of a1 up to aj minus 1 x aj plus 1 an, right? So a is a point. A is fixed. Be fixed. So a is a fixed point. So this is one variable function, right? Yeah. Call this gj. So gj is a one variable function. Yeah. Now, so suppose if it's differentiable in a domain, so you will get gj to be differentiable in an interval. Suppose let's say omega is some domain here. So this is omega is a domain in Rn, right? So what will be the domain of gj?
0, 0, R 0, 0. R is the jth position.
No. So suppose yeah. So, I mean, of course, here it is whole of R, but suppose f is defined on omega 2.
Pi j of omega, where pi j is the projection on the jth dimension. Pi j
Right.
of omega. Right?
Right. So f is suppose so here it is whole of Rn, so there is no problem. So here it is f whole of Rn, so this is defined whole of R. This is defined whole of R. But you may not have whole of Rn here all the time, right? You may not have whole of Rn here all the time. So suppose there is an omega here. So this is, so of course for simplicity we assumed this one so that you understand better. But you should understand this one also. So if then gj will be defined, gj is defined on collection of all a1, a2, aj minus 1, x belongs to R such that a1, aj minus 1, x, aj plus 1, an lies in omega, right? So it's basically the jth projection you are looking at from R into R, and you are looking at the image of omega. All right. So This may not be an interval, but you will have an interval in it. For every point, you will have an interval containing that point. Open interval, actually. All right. So now let's look at this one. So suppose in our case, come back here. F from Rn to R. So we can take omega also is differentiable. Right? Yeah, Krishnadas Saran, can you tell me whether the GJ is differentiable? Is GJ differentiable on R? GJ is defined as before here, right? GJX is f of a1 up to aj, comma x, aj plus 1, aj minus 1, this one, an. Yeah, Krishnadas Soren, are you there?
Yes, sir.
Yeah, can you tell me whether G is differentiable?
I think yes.
How you think? Also, so what is its derivative? Yeah. So what is its derivative?
Del f del xj at a1 into dot 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 aj minus 1 x aj plus 1 dot 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 a.
Right. So Gj prime x is del f by
Del xj.
who is speaking?
Me, Kayan.
Oh no, it was question for Krishnadas.
Oh, I thought the last question was for. Okay, okay, sure. Sorry.
And yeah, I mean, you know, right? So those who attended class already knew it. Yeah. So the problem is, if you don't attend the class, you just you don't get the definitions also. And this is an example. So del f by del xj of at, of course, this a1 up to aj minus 1 x aj plus 1 an. All right. So this is the derivative. So g is one variable function. So suppose, so if you restrict g in a closed interval ab, right? So which is from ab to r. All right. So we restrict g. So g is continuous on ab. G is differentiable on open AB, right? So then which theorem can we apply? Here
The
maybe
mean
I'll
value
just
theorem, right?
right,
Gm minus Gb is some G
right,
prime
right.
C.
So A is already taken, so let's call it CD.
Ah,
CD. So Yeah, C and T, and here C and T. Yeah, so now G is differentiable on CD, so we can apply the mean value theorem. Well, several mean value theorems, so the Lagrange is one. So we can apply mean value theorem and to get GC minus GD is equal to, so there exists a point alpha with the inside CD, interval CD, such that G prime alpha D minus C. Well, D minus C. So this form you actually seen it. All right. So now what does this represent in terms of F, right? So which is F of A1 up to AJ minus 1 D AJ plus 1 AN minus F of A1 A2 AJ minus 1 comma C comma AJ plus 1 AN is equal to G prime, which is del F by del F by del Xj at A1 up to AJ minus 1 alpha AJ plus 1 AN times D minus C. Yeah, is this correct? So you get a version of mean value theorem corresponding to each variable, right? Later we will try to combine these things together, and we'll give a statement in terms of gradients of function. So, but that will take some time. For the time being, what we get is corresponding to each variable, we can apply one variable mean value theorem, and we get a statement like this, right? So you can think this is a version of mean value theorem. All right, so this is true for every j actually, right? For gj I have chosen, but you can consider g from 1 to n, any j, right? Corresponding to each variable, you have an application of one variable mean value theorem to get this. So this you can think of a version of mean value theorem in higher dimension. All right. So with respect to one single variable, Rolle's theorem or whatever theorems you have proved there is valid. So real analysis, whatever you've learned in real analysis will come up here in each variable. So it would be an interesting exercise for you. Think of this one variable results, whatever you remember or whatever you liked that time, and you try to get it in terms of partial derivatives and see whether this looks something new or not. Yeah. So here, this is very simple, right? This is very, very simple. But now we will give an application of this one. So this is pretty useful. Though this is just application of one variable mean value theorem, but this is quite useful. So let me put it as a theorem, the application. got. If let maybe start it. Yeah, let f from Rn to Rm be a function so f is well, let us fix a point also, and a belongs to Rm. F is differentiable at a if all the partial derivatives del f j by del xk exists in a neighborhood of a and are continuous at a. So is the statement clear at least? So let us look at m equal to 1. Right, I have put it in general statement, but let us look at for m equal to 1. So what is it? If you look at m equal to 1, f is from Rn to R. F is a function and a is in Rn. Now the point is, we don't know if is differentiable or not. Our assumption is that the derivative del f by del xj exists in a neighborhood of a for all j. So suppose Rn is here. If you look at R3 or more, whatever. So now this is point A, and you have a small neighborhood around this. You have a small neighborhood around this where this function, this partial derivative exists and continuous at a. So this was one. Del f by del xj is continuous in a neighborhood of a. So if you shrink this neighborhood little bit, possibly you get the continuity of this derivative. Then both of this, actually this is saying that this implies f is differentiable at a. So the existence and continuity of the partial derivatives gives you the differentiability. Once it is differentiable, we get derivatives in terms of partial derivatives. Now we know that partial derivatives exist, but function may not be continuous even. Forget about differentiability, right? So we have seen this example, fxy is equal to xy by x square plus y square when xy not equal to 0 and 0 when xy equal to 0. So here del f by del x and del f by del y exists, right? On whole of R, at every point actually exist. At every point of R2, right? But f is not even not continuous at 0. Right? So forget about differentiability. Differentiability implies continuity. So this is not differentiable. So existence of partial derivatives does not give you differentiability. But if you add this, the continuity, add the continuity of the partial derivatives, then you get differentiability. All right? So note, if we add the condition that partial derivatives are also continuous, we get the differentiability. Right? We get the derivative map. All right. So this theorem is important. So showing some function is differentiable is now you don't need to look at linear transformation. You just need to show partial derivatives exist and partial derivatives are continuous. So for example, here by this theorem, any polynomial maps will be continuous. Sorry, will be differentiable. Yeah. All right. Now what we want to do is to give a proof of it. And in the proof, we'll use mean value theorem. So this is what we are going to use. So this is what we are going to use. So let me call this star. So this will be very, very useful to us. All right. Okay. So proof. What do we need to show? So we need to show the following. Limit h tends to 0, h is in Rn. So proof without loss of generality, we may assume that m equal to 1 as before, because component wise differentiability would give you differentiability of the total thing. Now limit h tends to 0, what we need to show is the following. Norm of f of a plus h minus f of a is a1 into an as before. A is a1 into an in Rn. Fa minus del fj by del f, because we have taken m equal to 1. Del f by del xj at a hj, right? And then you look at summation with j equal to 1 to n, and look at norm of h, and this you need to show 0. So is it understandable to everybody till now? Any question? All right. So we need to show this one. So we will focus on this part.
So one thing I'm not clear on. So previously we have already shown that if a linear transformation for the derivative exists, it's going to be of the form of that summation, right?
Right.
So doesn't that just show that if the partial derivatives exist, then it's going to be differentiable with transformation given by such and such?
See, this is the example, right? This is the example. Partial derivatives exist and f is not differentiable.
But then where is it going wrong? Because over there we showed that if the transformation exists, then it will be a...
Yeah, so we are looking at the converse now,
Oh, okay, right.
right?
Yeah.
So one direction is okay. If it is differentiable, then in every direction derivative exists. So which is partial derivatives. And once we know partial derivatives, once we know differentiable, derivative can be seen as the linear transformation can be seen as in terms of partial derivative. Now the partial derivatives existence of partial derivatives and getting that matrix doesn't mean that this will be the derivative of function, right?
Right, sir, got it.
Yeah. So to say this is derivative, what we need an extra assumption which is differentiability. Sorry, continuity of the derivative partial derivatives. So here what we need is the existence in a neighborhood and continuity. Continuity at A implies actually continuity existence of this, yeah, and continuous at A would give things. All right. Yeah. Okay. Now let us look at this. So this part, what do we focus on now? So f of a plus h, right, minus f of a. So what is this? This is nothing but f of a1 plus h1, a2 plus h2, an plus hn, minus f of a1, a2, an. All right. Now this one we actually want to organize in a different ways. So firstly, we look at f of a1 plus h1, comma a2, an, minus this one, f of a1, a2, an, this one. All right. F of a1, a2, an. Then we add f of a1 plus h1, comma a2 plus h2, comma h3, a3, an, minus f of a1 minus this first term, this term, a1 plus h1, a2, an. All right. Similarly, you add and subtract. Keep on doing that. So the last term would be just the penultimate term will be a1 plus h1, a2 plus h2, an plus hn, minus f of a1 plus h1, a n minus 1 plus h n minus 1, comma an. Yeah, is it fine? Is it visible properly? Yeah, is it visible?
Yes, sir.
Okay, so this is addition and subtraction. And what is the point? Point to use mean value theorem. All right. So what you get here, applying a star, you get what? The first term will be, so there exist points Cj. Well, yeah. So this Cj is in Rn. I consider the whole thing as point. So del f by del x1. So first one is the derivative with respect to the first one at C1. Right? So let me discuss what is C1 is. Right? So C1 is a point. So C1, let's say, yeah, let me put it on top. So this C1. So C1 is a point, there exists point Cj like this. So C1 is a point, something like this. So C1 is just C11, Cn1, where C11 lies in A1 to A1 plus H1, this interval. And Cj1 is just Aj for all j equal to j greater or equal to 2. All right. C1 is this one. So is it clear what C1? So we are using this first component, mean value theorem. Second remains same. Second onwards. And that is what it is. The second remains same. The first one changes. Right? And this will be multiplied by H1. This corresponds to the first difference. And then this will be again del f by del x2 at C2. So C2 would consider the first one will be just C21 will be A1 plus H1, right? So it is, this one will remain fixed, and this one we apply mean value theorem, and this remains fixed. H2 plus del f by del xn at Cn Hn. So all Cj have the property, all Cj have the property that Cj converges to goes to 0 as h tends to 0. All right. As h1, h2, hn goes to 0, Cj will also go to 0. See here C11 would lie in between this one. When h1 is goes to h1 going to 0, this C11 is going to a1. This is not going to 0. This is going to a. All right. All the Cj will go to a as h tends to 0. Is it clear? Yeah. So now consider one. Well, maybe I should not put one here. So this implies f of a plus h minus f of a minus summation over j equal to 1 to n del f by del xj at a Hj is equal to, now this one will have, see this one we started with what? This one. So we get this by using main Melo theorem. So this one is equal to summation j equal to 1 to n del f by del xj at cj, right? Minus summation, and then multiplication with hj is there, minus summation j equal to 1 to n del f by del xj at a hj. Now this one we can put summation j equal to 1 to n, and this del f by del xj at cj minus, well, this is not modulus yet, del f by del xj at a hj. All right. Now this implies norm of f of a plus h minus f of a minus summation j from 1 to n del f by del xj at a hj by norm of h. This one is equal to norm of summation j from 1 to n del f by del xj at cj minus del f by del xj at a hj norm by norm of h. Now this one we use triangle inequality, so less or equal to summation j from 1 to n mod of del f by del xj at cj minus del f by del xj at a mod of hj by mod h. Right? Now you take limit h tends to 0. So as h tends to 0, del f by del xj at cj, sorry, cj is upside, yeah, upper script, superscript. This converges to del f by del xj at a by continuity of del f by del xj at a. This is true for all j, right? So this implies and limit h tends to 0 mod hj by norm h is just 1. Yeah, this is an easy exercise to check, very easy exercise. You just look at the norm and expand it, root over x h1 square plus h2 square plus hn square, then you take hj common and take other things tends to 0. All right, so hence as h tends to 0, limit this norm of f of a plus h minus f of a minus summation del f by del xj at a hj j from 1 to n, this by norm h goes to 0. Is it clear? Yeah. Hence f is differentiable at a. Yeah, any question here?
Sir, I have a doubt regarding the exercise.
Yep.
Suppose we assume that Hj equal to 0. One direction, if I just specify Hj equal to 0, then that limit will be always 0, right? The whole of H need not be 0. H is going to 0, but the coordinate Hj is 0.
Right. The point is, question is whether the limit exists or not, right?
Sir, limit is bounded.
Limit is bounded by what?
Bounded by 1.
Okay. Right. Limit is bounded by 1. So that is quite good enough actually for us. Yeah, you are right. So actually, if you look at h tends to 0 and yeah, along directions where h is already 0, yeah, you got it right. So this is actually, this limit is not exactly equal to 1 all the time. This limit may not exist. But what you need is this is less or equal to 1. Yeah. So this limit may not exist. Well, limit will exist all the time, actually. Right. Yeah, no, that is fine. Limit may not exist. For example, yeah, each particular, let's say h1 equal to 0, you look at other coordinates going to 0, you will get the limit 0. But when you go other directions, let's say along h2 direction, you get limit to be 1. So limit may not exist, right? So thanks for this. So as h tends to 0, this holds. So this implies actually this, let's say 1 is less or equal to summation j equal to 1 to n modulus of del f by del xj at cj minus del f by del xj at a. Yeah, and which is going to 0. Yeah, any other question?
Times n, or is it just,
Hmm?
isn't it n times summation?
Why is it n times summation?
Each one is bounded by 1. I mean, I think it's okay if we take a small enough neighborhood. It will be.
Oh, well, you have summation, right? So each one you take which is less than 1, less or equal to 1, right? So here this one is less or equal to 1 for each sum, but for each summand actually. Yeah, each component of the sum. So you get less or equal to this whole summation without this HA by norm H.
Yeah, got it.
All right. Yeah, any other question?
Excuse me, sir, why will the limit not exist? I mean, for a particular j, the value will always be the same.
Okay, let's see. So this is, consider the function fxy if from, for example, from R2 to R, which is x by square root of x square plus y square, right? When xy not equal to 0. And you have to put 0 when xy equal to 0. Right? Now question is it continuous? Yeah. Is it continuous? Yeah, Ananya, can you tell me whether it is
No.
continuous?
Hello, sir. What's the question?
Yeah, whether f is continuous.
Uh, yes, sir. It's continuous.
So what do you think about continuity here?
The first one is 1 by root over 1 plus y by x whole square,
Hmm.
and
Yeah, but can you do this division by x?
yes, sir, because x is not equal to 0.
So what did you say? What did you get if x is non-zero?
Oh, both is non-zero. Yes, sir. I can't do because if it is 0 comma y,
So yeah, so xy not equal to 0, does it mean x non-zero?
yes, yes, yes.
Really?
X is 0. It can because uh, if y is not equal to 0, then also we can take the formula.
No, I didn't get it. Can you say it a little louder? So you're saying this xy not equal to 0
Sir,
means x
sir,
is not equal to 0.
no, sir. X can 0 can be because 0 comma y point will be there.
Right. Then what happens?
Then so wait a minute.
Yeah, Ananya, you should solve these problems from basic multivariable calculus as much as possible. I mean, this is very simple question to get stuck. Okay, so yeah, Aditya was saying something.
Oh yeah, I was saying I don't think it's continuous because you can
Yeah.
just approach it through the x-axis and the limit will be 1.
Yeah.
Like f of x comma 0 as x tends to 0 will be 1.
Right. So if I put instead of 0, if I put 1 here,
Still no, because then you approach it as f of 0 comma y as y tends to 0 and you'll get 0.
right. So this is not continuous. This function is not continuous, and even whatever you put here, you will not get continuity. Right? Can you put something and get continuity?
No, because like you're getting two different numbers as you approach.
Right.
You can never make them commensurate.
Right. So limit does not exist actually. So you look at y equal to mx along this direction. So limit x tends to 0, f of x comma mx. If you just put x by root over, so limit x tends to 0, x square plus m square x square, right? Which is limit x tends to 0, x gets cancelled. This is 1 by 1 plus m square, right? This is arbitrary depending on n, right? So this is just 1 by 1 plus m square. This depends on the direction you choose. Hence, this limit xy tends to 0, fxy does not exist. You can actually do it in terms of epsilon delta also, if you like. So this is actually implies f is not continuous at 0, 0. Okay, so what we have here is, so this part is less than 1 is very crucial. It should be bounded. That's it. That's what actually we want. Limit may not exist, doesn't matter. All right? So get it. Well, another application of mean value theorem. Suppose f from, let's say, R into R is a differentiable function while with continuous partial derivatives. Let A belongs to Rn be a point of local maximum. That is, there exists a neighborhood U of A such that mod of f of A is greater or equal to mod of fx for all x in U. Okay. Then del f by del xj. Well, actually the derivative df at A is 0. So what you need to show, proof? So use partial derivative. We want to show del f by del xj at A is 0 for all j. Right? Now A is a point here somewhere, let's say here. You consider this direction, you consider this direction, you consider this direction, right? Each coordinate direction. Okay? And you consider the function gj from R to R such that gj x is gj f of a1 a2 aj minus 1 x aj plus 1 an. All right. Now this gj a is just a1 a2 an. Gj at aj is greater or equal to mod. Did I take mod? No, I don't want mod. I don't want mod. It goes to R. Gj of x for all x in U intersection projection of the set x is in R such that a1 at2 aj minus 1 x aj plus 1 an is in U. Right? Now use one variable theorem. So G has a maximum at Aj. That implies Gj prime at Aj is 0. That implies del f by del x j at A is 0. All right? And this happens for every j. Hence, the derivative, which is del f by del x, derivative at A, which can be seen as a matrix form like this: x1 at A, del f by del xn at A, which is 0. Yeah. All right. So if you have any question, you can ask. Okay. So I'm done here for today.